Okay, so we're now in chapter 3 of the book. Okay. In chapter 2, we have seen there are 4 or 5 basic components that are present in the optical spectrometer. And in addition to the excitation source for emission, external radiation sources for luminescence, and absorption, sample containers, wavelength selection devices, and radiant power monitors, optical spectrometer contains a number of optical elements for collimating, focusing, and directing electromagnetic radiation. So what we're going to do in this chapter, we consider the optical components and systems used in spectrochemical instruments. So radiation sources and radiant power monitors will describe it in the next chapter. Okay, and the other components will be in the remaining chapters of this what we call book. So before we discuss the optical elements in detail, I think it's necessary to review several of these important optical relationships. We have met them before when we are introducing the course. So we can discuss it with these different basic laws in optics. So if we're going to look at this, we're going borderline optics today. So medyo may pagka-physics, okay? Or if you are in agricultural chemistry major in UPLB, I don't know if that course still exists, Physics 23, okay? That has what we call the optics, okay? So we begin with the discussion of the conservation of laws of refraction and refraction, which we have discussed already before, and the law of absorption. And then we're going to look at the phenomena of interference and diffraction. Okay, and we're going to go again about polarization, and we go into detail the application of this polarization, especially as instrumentation. Okay, so the modulators that we're going to discuss can be mechanical, electro-optical, acousto-optical, or magneto-optical devices. And then we're going to talk about mirrors and lenses that are used for imaging purposes in spectrochemical instruments. Okay, and the non-idealities which must be considered in their use are described. And we will talk about filters. Why are you not writing? Okay, so we're going to talk about filters. Okay, prisms, hindi siya, okay, and what we call other stuff, okay, like ratings. Those are that are commonly used for wavelength selection purposes, maybe in the next meeting that we have. Okay, and then we're going to look at maybe interferometers and other devices in the non-dispersive thing. So the basic law that we have, okay, we're going to discuss with what? The conservation law. Okay, so if you're going to recall the conservation law, maybe we can look at this as a basic principle of what? The wave motion. Okay, so if you're going to look at the basic principles of the wave motion, so we could say that it has, it follows this what we call a conservation law. So the basic principle of the wave motion is that when a wave strikes a boundary, okay, between two media, a portion of the wave is reflected, a portion of the wave is absorbed, and a portion of the wave is transmitted into the new medium. So you could say conservation law, okay? Because if you have a wave, what will happen? Reflection, absorption, bakit ang pangit nito? writing pad go? Just turn it on and then off and then on. Now I know. So if I got that, I have to get the cable. There you go. So reflection, absorption, and transmission. So if you're going to add all of them, those are the waves that came to a given sample. So one basic principle that we have there is you're going to conserve that, okay, in terms of what we call wave. So a portion of the wave is reflected, a portion is absorbed, and a portion is what we call transmitted into the new medium. So this is known as the conservation law. So consider the radiant energy of wavelength. Okay, and what happened is it is to be an incident on a boundary between two media. So the portion of the incident radiant energy lost by absorption, okay, in that interface or surface is known as the spectral absorption. Okay, so this is the fraction, okay, of the incident energy lost by absorption at the interface or surface. Now, the fraction reflected, so we could say this is the one that is absorbed. Okay. Now, the one that is reflected, okay, so this is the fraction reflected at the interface or what we call the surface. So that is the spectral reflectance. And last but not the least, you have the so-called spectral transmittance. Okay, so this is the fraction transmitted into the entered medium. And if you're going to look at the quantitative statement of the conservation of law, how does it look like? We're just going to add all of them. And they should be equals to what? Anyone? If you're going to look at the quantitative statement of the conservation law. So if we're going to add all of them, this just equals to 1. The amount of the wave that strikes the what we call boundary between the two media. Okay, so that is where we have this what we call conservation law. Now, this conservation law, they have practical consequences in spectrochemical measurement. In the absorbance or in the absence of the significant reflection at an interface, the spectral absorbance is given by what? If there is no reflection, how can we get the spectral absorbance? So maybe we could say that this is 1 minus, there's no reflectance, so you can put it like that. In the absence of the absorption, the spectral reflectance is going to be the other way around. So if absorption is not there, so you can put it like this one. Okay. And in the absence of any transmission in this what we call second medium, the conservation law tells us that the absorbance is equals to 1 minus the transmittance, the one that you have here, the P. So if you have it like that, okay, minus this one and then P minus that one. So if the one that is absent is what we call transmittance, okay, in the absence of any transmission of the second medium, what will happen is the conservation tells us that most likely this is what you have. Okay? So that is, we could say, the conservation law. So if there is no transmittance in the second transmission and there is no absorption, what will happen? Kapag wala yung transmittance saka absorption, what will happen? Okay? So everything is equals to this, what we call this, or unity, if you don't have this one and this one. So if you're going to look at the conservation of law, it's just trying to, we could say, take into consideration what happened to the wave as it passed through what we call two media. Okay, so some will be reflected, some will be absorbed, and some will be what we call transmitted. Okay, so let's go on the law of reflection and refraction. Okay, so if you can remember, James Maxwell, okay, showed that the velocity of all electromagnetic waves in free space is equal to what? The speed of the light. And it can be described theoretically, okay, as C is equals to, if we're going to look at that, what we call definition, C is equals to 1 divided by this one and this one. Now, what do you call this? And what do you call this? So this is the so-called electric permittivity, and this one is the so-called permeability. Okay, so all of them we could say are of free space. Okay, and out of this, what's the value that you can come out in this speed of light? Usually you end up with 3 times 10 to the 8 meters per second. Okay, and we can say that based on the absolute index of refraction given by this what we call symbol, the ratio of the speed of light or an electromagnetic wave in vacuum to that in matter is over this one. Okay, or if you're going to discuss it in terms of this permittivity times permeability, okay, of a given matter over permittivity and permeability of the free space. Or if you're going to simplify it, this is what you get. Okay, so this one would refer to the space. Now, what do you call this? KD. Anyone? I think you encounter it in other parts of instrumental analysis. What is usually KD? KD is what? I think in Orgo you encounter it as, is that the one organic over water or aqueous? Naririnig niyo ba ako? What is KD here? So that's what we call the dielectric constant. Okay. So if we're going to look at this, what we call the E, something to do with the permittivity of a medium related to that of the vacuum or the free space. So we could say, how do we put this? E equals to K E over free space. So what do we do? This is the KB, okay? And we can also put here, in terms of M, the permeability equals to Km times the permeability of what we call the free space. So what we do here is from this expression, okay, we just simplify it to this one. So Kd, that's your dielectric constant, and Km, that is your relative permeability. Okay, so in short, your refractive index can be written as Kd, square root of Kd times Km. Now, the question is, what can you say about this refractive index? If you're going to look at the refractive index of the medium, how does it is related to the wavelength of the incident radiation? Okay, so we can look at it that since the refractive index of a medium varies somewhat with the wavelength of the incident radiation, so we can have the phenomenon known as this, what we call dispersion. Anyone heard this term before? Class? What have you known about this so-called dispersion? Anong we could say simple explanation ng dispersion? Okay? Because here I could say variation of refractive index on a medium with the wavelength of the incident radiation. So we could say media that are colorless and transparent, they have a characteristic frequencies of oscillation, the natural frequencies of the atomic and molecular oscillators in the ultraviolet. Now, if you're going to have glasses, for example, they may have characteristic oscillations at wavelengths near 100 nanometer. Okay? And for these materials, usually the refractive index increases as the radiation frequency approaches a natural oscillation frequency known behavior as the normal dispersion. Okay? So what is really dispersion? Have you heard it before? So how do we could say explain what is seen here? What can you say about colors? Do you expect colors to travel at the same speed? Say for instance, blue versus red. Do you expect blue and red to travel at the same speed? So let's say, imagine you have a beam of what we call white light. It passes through a prism. And what will happen there? In normal dispersion, what will the prism do? The blue is faster than what we call red. So if you have a white light, it passes through the prism. What will the prism do? It will disperse different colors. It causes the prism to what? Spread out some color, forming the so-called rainbow. Am I right? Okay, so it disperses light into a different color. Okay, so what do you think happened? Let's say in the glass, when sunlight passes through a glass prism or a raindrop, what do you observe? When do you usually see the rainbow? Nakikita mo ba yan pag tag-init? I don't know if tag-init na dyan sa inyo. You only see the rainbow after what? A rain. Di ba? So if you're going to look at this common materials, like let's say it's a glass, okay, or let's say it's a raindrop. So when the sunlight passes through this what we call raindrop, you observe a rainbow with the blue and the violet appearing on the inner side of the arc, okay, closer to where the light enters the material. So when we're talking about dispersion, that's what we do. Separation of colors, okay, due to different speeds in the material. So yung blue yung pinaka what we call mabilis. Okay? So normal dispersion is where you have the separation of colors of light due to different speeds that you have there. Okay? And if you're going to look at the effect here of the medium, so in a medium of refractive index more than one, a wave of frequency undergoes a reduction in the wavelength compared to that in vacuum. So the wavelength in the vacuum is equal to wavelength over velocity over the frequency. Okay, or we could say speed of light over, okay, the refraction index times the frequency. So when a wave goes from a medium of refractive index N1 into a medium of refractive index N2, the ratio of the wavelengths in the two media is given as wavelength 2 over wavelength 1 is equals to the reciprocal of refractive index 1 over refractive index 2. That's the wavelength is that smaller in the medium of the higher refractive index. Okay, so what explains this? This is explained by Snell's law. Okay, so as I told you, this is already discussed before. Okay, so the Snell's law, we could say that's the one that describes the refraction, as you could see here. And if you're going to see here, the Snell's law of refraction is diffraction 1 times sine theta 1 is just equals to diffraction index 2 times sine theta 2. Okay, and if you're going to look what is happening here, okay, so when okay, so that's a wrong. There you go. So if you're going to look at the wave that is happening here, so here is a ray representing the reflection and no, this is one reflecting the both the reflection and the what we call refraction. Okay, so if you're going to look at this from the what we call representation, so we could say you have this, say passing through there. So what is this? What is this phenomenon going here and then here? That is usually your what? Refraction or reflection? Okay, yung pag ganun, the bouncing. of the wave. I think it's part of the quiz. Okay, that's reflection, reflection. And then this one, from one media going to this one, okay, so that is what we call your refraction. So here you're going to see this one here and this one here. And then you have the diffraction index of the first medium, and then the diffraction index of the second medium. So a ray bends toward the normal, okay, so theta 2 is less than theta 1 when it enters a medium of higher refractive index, and away from the normal when it enters a medium of a lower refractive, what we call index. Okay, so if you're going to look at this, you could see that there is some loss of reflection at the interfaces. Okay, so try to imagine when you're doing spectrochemical measurement. Okay, so usually, what do we have? We have to put your sample in what we call a sample holder, or the so-called cuvette. Okay, so what happened? How many mediums that it has to pass through? Usually there's two mediums, the air and the glass. But if you're going to do air, glass, and then what? Your sample, glass, and then air. Okay? So what happened here is you have radiant energy that's transmitted across one or more interfaces, separating the dielectric media of the different refractive index. So as I told you, there's two air-glass interface to traverse when your light pass through a lens. And in the measuring devices that we have a cuvette filled with solution. So there are two air-glass interfaces and two glass solution interfaces. So saan yun? Okay, so air and then glass. Okay, and then you have what? Glass and then solution. And then glass and then solution, and then glass and then air, or solution and glass. Okay, so any radiation that is reflected on the interface will cause a loss in the radiant power transmitted into the new medium. Okay, so how does you consider the effect on this one? How do you consider these losses of reflection at the so-called interfaces? Okay, because if we have your setup, you're going to have radiation that is what we call reflected at the interface, and this will cause a loss in the radiant power. Now, if the incident beam is monochromatic and normal to the interface, the reflectance is going to be given by this equation. So what is this? Based on sa binigay ko sa first slide or second slide about this conservation law. Spectral ano siya? This is your spectral reflectance. So when the incident beam is monochromatic and normal to the interface, the reflectance is given the so-called Fresnel equation. So what can you say about the Fresnel equation? It's just rearrangement of your what? Refractive indexes. Okay. So it is just equal to the ratio of the difference of the second refractive indexes minus the first refractive indexes over the sum, and then you get the square root. And when N1 is equals to N2, there is no reflection. Okay? So when N1 is equals to N2, what does it mean? This value is equals to 0. Okay? Now, for the cases that we have, the air and glass interface, so the refractive index of your air is 1, and that of the glass is 1.5. So you get around what? 4% of the light incident that is perpendicular to the interface that is reflected, and 96% is transmitted unless an anti-reflection coating is applied. Can you try? If this is the value that you have, if you really get 4%, the one that is what we call reflected, now, in the case when there is what? In the case that there's unpolarized radiation strikes the interface at an angle other than 90 degrees, the reflectance varies with the angle of incidence according to the Fresnel complete equation. And this is the Fresnel complete equation. So here, we could say here that the theta 1 that you have, that's the angle of incidence, and theta 2, that is the angle of refraction that is measured with respect to the normal surface. Okay, so if you're going to look at here, okay, you have the sine squared, the difference of the incident light and reflection angle of refraction over sine squared, the sum of the two, plus tangent squared times this over this one. So if a beam strikes the interface at an angle other than 90 degrees, reflectance varies with the angle of incidence according to this equation. And here we have a plot showing, okay, reflectance versus the angle of incidence for a monochromatic beam traveling from air that gives refractive index equals to 1 into glass with the refractive index 1.5. Okay, so if you're going to look at this, note that the reflectance changes only slightly up to an angle of 60-degree angle, and then increases rapidly until it is 100% at grazing incidence. Okay, so you have here this what we call reflectance versus angle of incidence. Okay, so if you have here for A, that is what we call unpolarized. Okay, now for B, okay, that is equals for the perpendicular polarized. And the C there, that is for, what do you think? Parallel polarized. So see the difference there, okay, of your reflectance versus the angle of what we call incidence. So note that the reflectance of these perpendicular components always exceeds that of the parallel component. Okay. Now, there is also a chance where the reflectance of the parallel components becomes 0 at a particular angle, and that's what we call the Brewster's angle. So the Brewster's angle, that's where the reflectance, okay, of parallel polarized parallel components becomes 0. Where do you observe that? maybe can we consider this as 0? Okay. So I think that is what you call the Brewster angle. Okay. Now, we have this what we call total internal reflection. I think we discussed some of it before. So if we consider the transmission and reflection of the radiation where the source is in a medium of refractive index 1, N1, that is larger than refractive index N2 of the transmission medium, what we have here is looking at the Fresnel complete equation. It tells us that the transmitted radiant flux is a maximum when the incident beam is normal to this what we call surface. Okay, so if we're going to look at the here, so maybe what the incident beam is in a medium with a refractive index 1 that is greater than the transmission medium. So what will happen? So in A, if we have this condition, when the incidence beam is in a medium of a refractive index greater than that of the transmission medium, so what happened in part 1? Anyone? The letter A. What happened to your beam? Your refracted beam? Usually, if you're going to look at this, they bent away from normal. Now, what happened in the second one? What happened to your angle of incidence here? Compare it to the first one. Go down or go up? So as it go up, what happened to your refracted beam or reflected beam? So where is the reflected beam here? This one. Okay. So as the angle of incidence here goes up, your reflected beam, they grow stronger. And what happened to your refracted beam? This is stronger, and this one becomes weaker. Okay. Now, how about here? 90 degrees. So this is an angle of incidence equal to 90 degrees or exceeding, because here I show here 90 degrees, and here it is exceeding 90 degrees. Okay. Your critical and the angle of cedar, the transmitted beams become zero. So if you're going to summarize again what happened here, okay, in the total internal reflection, so we look at the incident beam that is, we could say, in a medium of refractive index greater than that of the transmission medium. Okay, so in part 1, your refractive beams bent away from the normal. In the second part, your refracted beam grows stronger and the refractive beam goes weaker as the angle of incidence becomes larger. And then at angles of 90 degrees or greater, the critical angle, okay, the transmittance beam intensity goes to zero. When I say the critical angle, this one. So it becomes what we call the transmittance beam goes to what we call zero. Okay. Now, the question that we can ask ourselves, where do we use this? What's the application that I mentioned about the use of total internal reflection? Anyone? Okay. Optic fiber or the fiber optic. So that's where you utilize this, what we call concept. Okay. Now, the next thing that we're going to discuss has something to do with what we call absorption law. So another process that can affect radiation is the absorption by the medium. Okay. So in the absorption process, your atoms or molecules in the medium are what? Excited. And the energy absorbed can be dissipated as thermal energy, radiant energy like luminescence, or chemical energy if you have this so-called photochemical reaction. Now, the amount of the radiation absorbed depends on the total numbers of absorbers that interact with the beam. And we should not be surprised, okay, that the amount of radiation absorbed depends on the thickness of the medium and the concentration of the absorbing species. Okay, so based on the thickness and the concentration that you have here. So if you have the thin slice of the absorber, so it can depend here. Okay, so if this is your incident light, so it can be absorbed here. So the amount that you have here, okay, is just minus, okay, the number of the absorbers that is usually what? Proportional to the thickness of the slice. So the thicker of the slice, okay, the higher the amount that is what we call absorbed. Now, since the number of the absorber is proportional to the thickness of the slide, so what do we have? We're going to have this relationship. Okay, this with respect to this one and dB. So this is your absorption coefficient. Now we have a negative sign that's due to the beam attenuation, which increase with what we call thickness. So doing this integration that you have here, okay, you end up with this what we call relationship. So to obtain the absorption in a medium of finite thickness, so that's B, okay, we can rearrange this above equation into what? Integral? Kalimutan ko yung math. So this is what? Integration, your integral, okay, integrated from zero thickness, where the incident flux that you have there with respect to the thickness where the transmitted, this is the transmitted flux that you have. And you end up getting with this relationship. And out of this, okay, we can say that the absorption coefficient, that is K, the magnitude of it depends on the wavelength of the incident radiation, the nature of the absorber, and the concentration of the absorber. Okay, so in atomic spectroscopy, the absorption law that is most commonly used is in this form. That is the one that is commonly used in atomic spectroscopy, where K is what? Dependent on the concentration. Now, in molecular spectroscopy, it is common to state explicitly that the concentration dependence of the absorption expression coefficient by expressing K as equals to K prime C. So we could say atomic spectroscopy, that's the one that we have, this one, yung walang prime. But for the molecular one, okay, we put that this one can be similar to that, okay, and this is what we have. That equation that you have here becomes this one. So you have here an extra concentration, okay? And most often, in absorption spectroscopy, we measure what? The transmittance. The amount that was out and over the amount that was input, okay? So if the transmittance is 100%, what does it mean? There is no absorbance, right? Tama ba tayo? If there is 100% transmission, nothing is absorbed. Or, if we're going to take it in terms of this absorbance, that's just negative log T. Okay? And this becomes a constant to a particular species, the molar absorptivity. Okay? And we end up with the absorption law like this one. So I think everyone knows about this. Am I right? What do we call this? Ano na tawag natin dito? Anyone? Absorbance law ang tawag dati, di ba? But now we call it the Beers-Lambert law. Beers law, or also known as the so-called Beers-Lambert law. And we could say this is one of the most useful equation that we have. Usually, what did they develop? If you wonder sometimes, how do they measure some of the analyte in your urine or your blood? So usually what they do, the company has already developed, okay, and patent most of these reactions. So what they do, they react, take your sample with a coloring agent, and whatever they produce, they already know the molar absorptivity. This is fixed. So whatever the absorbance that you get from your sample, okay, you divide it with the molar absorptivity that is already known, and the path length, the length of the path or path length, okay, and you'll be able to get the concentration. So this is one of the things that we're going to be useful. Okay, so if you're going to look at the statement, okay, believe it or not, there are what we call statement of assumption of the absorption law. Okay, so the first thing that you have here is the incident radiation is monochromatic. So what does it mean? There's only one wavelength. Okay, so usually you use where you get the highest the wavelength that will give you the highest absorbance. Now, the absorbers that you have, molecules, atoms, ions, etc., it acts independently of each other. Okay, so if you have absorbers there, okay, they are independent. Now, The incident radiation is consists of what? Parallel rays perpendicular to the surface of the absorbing species. So everything parallel and perpendicular to the surface, right? And the path length transverse is uniform over the cross section. What does it mean? You cannot have it like this. What do you think the absorbance on this area compared to the absorbance on this area? Anyone? So which has a higher absorbance? If we have a container like that one. Anyone? Ano sa tingin nyo? Alin yung mas mataas yung absorbance? Yung dumadaan sa A o doon sa B? Okay? So usually the A has a higher absorbance because of the path length. Okay? May effect yung path length. Kaya dapat uniform over the cross section. And then the absorbing medium is homogeneous and does not scatter the radiation. So what does it mean? Ano kailangan yung sample mo? What does this statement tells us? Okay lang may solution? Okay lang solution as long as wala siyang solid particle. Because the solid particle can scatter the radiation. So you want it to be just homogeneous, the same color. I remember one experiment. I'm always what we call surprised why the reading doesn't make sense. And yung pala ginawa ng mga bata, nandoon lang yung ano, hindi nila hinalo. So, ang nadadaanan lang ay yung hindi color because they have to at least mix it so that it will become uniform. Remember when you do like a calibration curve, right? So they have a cubette. So they put different volume there and then add water. They didn't mix. So the reading that they have is not uniform. So right away, like I said, why is it not increasing? It should be increasing. And then last, the incident flux is not large enough to cause saturation effect. So when you're talking about saturation effect, that's what we call laser. Because what happened, based on my experience, I burn or I toast the detector because of the incident flux. So we use laser. So the incident flux gave too much power. So ang nangyari dun sa detector, sira. And it happened when the first time I used a laser. Yung bigla na lang ang taas ng energy and then all of a sudden zero. And then the next reading that we get is all zero. Now, what else that we need to remember here? So I think we need to remember also in this portion, okay, the container that we have. So usually, what do we have? Quartz, glass, and plastic as the one that we have as cubette. So which one is applicable in all wavelengths? Alin yun applicable in all wavelengths? Usually this one. It can go to what? Maybe 180 to 800. Glass, we can go around what? 300, I think. And this one just go to the colored one. Okay? So that we could say the three laws that will dictate the components that we're going to discuss at least here. So the next thing that we're going to do is the phenomena of interference, diffraction, and polarization. We already discussed this, but I just want to show you ano yung instrumentation out of this concept. Next slide. Wala namang celebration ngayon. Okay? So if you're going to look at this phenomena, they all deal with what occurs when you have two or more electromagnetic waves that overlap at some point in space. Okay? So what we have here can be like the general concept of superposition of waves. We consider it first, and the production of the so-called overlapping waves through interference and diffraction. And then the polarization of the electromagnetic radiation and the phenomena of optical rotatory dispersion and circular dichroism. Okay, so we go first with the so-called superposition of waves. So what happened here? These are the superposition of the sinusoidal waves. So what can you say here on the first one? You add two waves, like E and E1. Okay, there are two what we call constituent waves, and they are in phase. So they have the same what we call the wave here. So what will happen? They're just going to produce a much higher wave. It's just like what? Addition. So if you combine the waves, what will happen is you're going, if they are in the same frequency, okay, you're just going to have a much higher wave. Now, how about happen on the second one? You have the first wave that is here, and then you have the second wave that is here. So in the first one, you produce a higher amplitude. In the second one, you produce lower or smaller amplitude. But in both cases, you're just adding both of the waves that you have there. Okay? So this is, we could say, the superposition of waves. So superposition of waves is just an example of a transverse wave. In that direction of the vibrating electrical and magnetic fields are perpendicular to the direction of the propagation. So if you have waves that have disturbances along the direction of propagation, like the sound waves, okay, you have there by contrast what we call the longitudinal wave. So a transverse wave is said to be what? Plane polarized or linearly polarized. If a fixed plane, the plane of vibration contains both the vibrating electric field and the propagation vector. Okay, so if we're going to look at here, so you have here like they are the same, so it becomes higher. But here, one of them is here, the other one is here. So what happens is you're going to have what we call a much lower one. Okay, so based on this, what we call superposition of waves, you can have this so-called constructive interference. So in the constructive interference, it happens when the optical path length difference is an integral multiple of the wavelength. And you can also have a destructive interference that occurs when the difference you have here. So we could say this is what? Constructive, and this is destructive. But sometimes if you have the destructive like this one, ano yung nangyayari? Wala. They all cancel out. Why didn't we notice it here? Bakit hindi to completely zero? Anyone? Because if you're going to look at E1, its amplitude is not the same as the E2. But if the amplitudes are just the same and they're just not in phase, then your destructive interference here will just be a straight line. Constructive interference on the other way, they just get what? Higher. Now, this leads us to this what we call optical interference. So optical interference, this is just interaction of light waves to yield a resultant radiance that is different from the sum of the component values as predicted by the principle of the superposition of waves. So two waves for which the initial phase difference is zero or constant for a long time are said to be coherent. But waves emitted by separate sources are incoherent with respect to one another. Okay? So what are the conditions for the interference? So these are, we could say, the three conditions that you have. The light reaching the point of the interference comes from a single source by two different paths. And then the second one, the interfering waves have very nearly the same frequency composition. And this again, okay, is readily achieved if the radiations come from a single source. And then the normal unpolarized light also produces interference. So how do we observe this, what we call interference? So imagine you have, we could say what? Two or more waves. And when they meet and they interact with one another, okay, that's where we could say interference happens. So the result can be what? The reinforcement of the waves or the cancellation of the waves. And if there's a reinforcement and the cancellation, what is the pattern that you're going to observe? Bright, dark, bright, dark, bright, dark region. Okay, so imagine you have two pebbles. You drop them simultaneously into the pond. So what will happen? Each pebble will create a ripple that will spread out. Now, what happens if the ripple from both pebbles overlap? What do you notice? Either the pebbles will combine or the wave from the two pebbles will combine and you will have what? A much larger wave. Or, okay, they can cancel out. So the one where you have these pebbles that, the waves that become larger, that is a constructive interference. The one where they cancel out, that is the destructive interference. So that's what it means here on this, what we call interference. Now, even the normal and polarized light, that is also what we call produce interference. Okay? Now, the thing that I want to go to, we have a definition here, coherent and incoherent. What does it mean? Is this the first time for you to what we call encounter this term? What does it mean? Anyone? Coherent. Anyone wants to try? Two waves for which the initial phase difference is zero or constant for a long time are said to be what? Coherent. Okay? So, ano ibig sabihin yan? Can we say synchronized? So usually, pareho lang yung mga yung wavelength nila, yung waves nila from the initial, okay? Yung difference nila is zero or constant for a long time. So they are in synchronized, we could say, situation. And usually, if you have coherent, this will always lead to what? Constructive interference. Okay? And I try to introduce this to you because you will always hear this word coherent when you're using what we call laser. Laser light is an example of a coherent light. Okay? They always have a single line or a single wavelength. The waves in the laser beam, they're well organized and synchronized, allowing them to create a powerful and focused beam. Any one of you has used a laser already in your life, except the laser pointer, okay? I think most of you has what we could use a laser pointer, but I mean the laser that is used in research, it's not the same as the laser gun, okay? Now, if we're talking about incoherent waves, they are what? They're not synchronized, okay? So in terms of the waves, they may have different frequency, wavelength, amplitude, so they don't align. Now, this lack of alignment can result in what? Random interferences. It can reinforce or we could say cancel each other. But the thing is, it's unpredictable. And what is the example of the incoherent light? Anyone? Ano sa tingin nyo ang best example ng incoherent light? So if this is laser, so what do you have here as an incoherent light? Anyone? Come on, you experience it every day. Walang sasagot? Ha? Sige nga. Coherent po, sir, that's laser. So what about incoherent? Light bulb? But I think the best example is the mother of all light, sunlight. So that's because I just want to see, because you're going to encounter what's this coherent or incoherent thing. I think one company of laser is really named Coherent. Okay. Now let's go with what we call a diffraction. So diffraction, we could say deviation of the light from a rectilinear propagation, which it encounters an obstacle. So we could say a parallel beam is bent as it passes by a sharp barrier or through a narrow opening. So when this happens, your parallel beam tends to slightly spread slightly on the passage to a narrow slit. And then we can also say that some of the electromagnetic radiation waves, they always what? Spread out. Okay? To some extent into the region which is not directly exposed to the coming wave. So the distinction between diffraction and interference is somewhat what? Arbitrary. Because diffraction can also result in superposition of waves. Now, interference is usually considered to be superposition of only a few waves, whereas diffraction is considered to be that of a large number of waves. So that's the difference. Few waves versus lot of waves. So this optical phenomena of diffraction can be explained by assuming that the radiation wave moves through space in a linear wavefront. And each point on the wavefront, they can be regarded as a new source of waves called the wavelength. Now, these secondary wavelengths, they're propagated in all diffraction with the velocity of the original wavefront. And this principle, the Huygens principle, in conjunction with the phenomenon of interference, is used to explain the features of this, what we call diffraction. Okay, so diffraction is just the phenomena that happen when waves encounter an obstacle or pass through a small opening that cause them to spread out or create a pattern of either bending or in some way interference. Okay. Now, the key points about the diffraction is what it is in terms of light. Okay. What do you remember when you say the encountered the name Huygens, Christian Huygens? He established what? The wave property of light. And this is due to this, what we call diffraction. Okay. Now, if you're going to look at this diffraction, so maybe now you will remember his name, Fraunhofer diffraction. So usually this is a diffraction by a slit by what we call Fraunhofer. He didn't invented the diffraction grating. It was already exist, but what he did is he made use of it. Okay. So in the diffraction by a slit, so the diffraction pattern observed on a plate or a screen by a slit would be alternate light and dark bands called fringes. And in the next figure that we have in the next slide, the relative intensity of the bands of light is represented as peaks, with the central band having a maximum, okay, at P0, because the interference between the wavelengths from the slit is constructive for the direction directly ahead, where the angle is equal to 0. However, destructive interference between wavelengths causes intensity minima at points P1, P2, P3. So if you're going to look at this, this is what it means. Okay, so you have here a small slit, and you let a light passes through. So the source is placed at a long distance, so the rays will be parallel. So if it passes through here with a single slit here, so you see that the rays from the slit at reach here all have identical optical path length. So if you're going to look from the center, going down and going up, they have the same path length. And the one that's always here is the one that gives you the highest. Since they are in phase, in the plane of the slit, they are still in phase at this position. And that gives rise to the central maximum of the irradiance. So here you have what? Based on the Fraunhofer diffraction by a single slit, your parallel source rays illuminate the slit where the diffraction happened, and the observation of the light a large distance or focused by a lens yields a diffraction pattern, and the diffraction is minimum at P1. That one there. Now, what happened here? So there are two rays that reach P1, this ray and this ray, okay? So if you consider these two rays that reach this area here, so the ray originating at the top of the slit must travel a distance of x equals to W width over 2 sine theta, farther than the ray from the center of the slit. So one here in the center and the one over that one. So according to the earlier discussion, a destructive interference is expected when the difference is lambda divided by 2. Thus, the minimum irradiance occurs when we have this W2 sine theta equals to wavelength of 2, or W sine theta equals to what we call the wavelength. Now, what if you have more rays like this one? So you can have other minima by dividing the slit into what? 4 parts as shown here in this what we call figure. And any adjacent rays will destructively interfere when the width divided by 4 times sine theta is equals to the wavelength over 2, or W sine theta equals to 2 times the wavelength. And then by extension, the general formula for diffraction minima is this. Given that M is what? Plus 1, plus 2, plus 3, and so on. Now, to achieve the maximum advantage of this grating, okay, diffraction grating or prism for separating this mixture of radiation into its component wavelength, the entire side of the prism or length of the grating should be illuminated. And when you do that, there will be optimum slit width that will just allow the central maximum intensity band to be focused on the entire length of the prism of grating. And when this, it becomes what? W equals to sine theta, which is equals to the wavelength. So when W becomes narrow, too narrow, okay, what will happen? What will happen to the central band? Usually, it will be missing both either the grating or the prism, and it will just be what we call wasted. But if the width is too wide, you can have a maximum use of your grating or prism. But the thing is, it's not also good, okay? Because you will have some dark region adjacent to the central band that will be, we could say, focused on the dispersion device. So the optimal slit should just be like this. So this is like the thickness before that we have discussed in the absorbance law. So this is just the width of your grating or prism to be illuminated. And then the D here, that's the distance between the slit and the grating or prism. Okay, so it cannot be too wide, it cannot be too narrow. So when m is equals to 1, your sine theta is equals to lambda or wavelength over what we call the width. And as W, as the width decreases, your angle there, your theta increases and the beam spreads. So if we consider the angle to be small, then the angle that we have should be the wavelength divided by the width. And what we have here is the angular half width, or width at half maximum intensity of the beam. In this case, is said to be diffraction limit. So the width cannot be reduced to zero unless W is infinite or wavelength is what we call zero. You usually do this when you try to determine, okay, at what wavelength you can get the maximum reading. So you have this total beam half width, W prime after the beam travels a distance of B, and it's approximately original width plus B times the angular width. So wavelength over the width. So for large enough B, we can neglect the original width, okay? And the plot of the irradiance of a diffraction beam upon striking a beam is shown here. So this is the one that you want. Oops. And this is what from hyper diffraction at a single slit. Noon, mano-mano mong gagawin yan. But now, there's preset already. What's the problem usually if you use this kind of thing? Whenever you use laser, what's the main problem that we have? Anyone? Any of you experience using laser as a light source? If you don't have any patience, you cannot use this one. Because the thing that you have here, if you have a diffraction rating, is you need to do this. You align it until you see the highest signal that you can get. Alam niyo sino magaling dyan? Si Marvin Bilog. Ang galing niya mag-align ng laser doon sa lab. Hindi ko alam kung kaya pa niyang gawin ngayon. That was before pandemic. Okay? You should try to what we call adjust the slit, okay, until you get the thing. And you can also have a multiple slit diffraction, because what we did is what? A single slit. Now, if you increase the number of slits, each diffraction maximum grows in irradiance and becomes narrower. And the narrowing occurs because the multiple slits only a slight change in the angle wave from that almost corresponding to a maximum leads to almost total destructive interference. So we could say the diffraction ratings may be considered to consist of many closely spaced slits, and such ratings can be what we call considered here. So look at the thing that is happening when you have this multiple slit. So if you're going to have here, how many slits do you have? Ilang slits meron? Anyone? If I put this in the quiz, how many slits do you see? How many slits do you see? Class, ilang slits? 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there are what we call 6 slits here. Okay? So the 6 slit diffraction there separated by distance what? D. So that's the D that you have there. Okay? So what happened here? Your light rays will reach one point on the screen as shown in this one. So isa lang yung ano niya, lahat sila papunta doon sa isang point. Compare this one, okay? Your irradiance pattern of the screen is shown for n number of slits. So for large n, each principal maximum has the same what we call shape of the slit. So what is the result coming from this? So maybe like this one, depending on the distance. But for this one, if you have large n, so this is what you have, the B. Okay? So the difference here of your OPL between adjacent rays is x times d sine theta, where d is the distance between the slits. So you can have a maxima in the irradiance when this distance is an integral multiple of the wavelength, like n equals 2, n equals 4, and then you will see the difference that you have here. So that is what we call a multiple slit. So as the number of the slit increases, each diffraction maximum grows in irradiance and it becomes narrower. So the narrowing occurs because the multiple slit only a slight change in angle away from that corresponding to a maximum leads to the total destructive interference. So which one do you prefer here? This one, or this one? Well, it depends on the data that you're looking for. But as you could see, as the number of n decreases, okay, the signal that you get becomes narrower. So, yep. So I'll end here. And then we're going to discuss, hindi umabot dito sa plain polarized, because I'm going to discuss like the polarimeter, the circular dichroism, and then I might add more slides, okay, as we go on. But I think we're getting to what the instruments would really, we could say, look like. Question. So I'd like to thank everyone who already posted their